In the previous video, we looked at how the movement of Na plus from a high concentration outside of the neuron to a lower concentration inside of the neuron results in both the outside and the inside of the neuron's membrane becoming positively charged. And this is the idea of depolarization, and also how this depolarization spreads from the origin of where the stimulus began all the way to the end of the axon termini. Now, what we're going to look at in this part here is how the neuron is able to reset itself in order to be able to fire again. Now, in the previous video, we looked at the significance of the maximum voltage, whether it be positive 30 or positive 40 millivolts, depends on which graph you look at here. But the point is that at this maximal voltage, this is the point at which not only have we achieved an isotonic concentration, where the concentration of sodium outside and inside remains relatively equal, but this is also the time when the voltage-gated sodium channels close, thereby preventing sodium from being able to get in or out. However, if we remember the background of what type of ions exist inside of the neuron, we also need to remember that potassium ions exist in a higher concentration inside compared to outside. And as the voltage-gated sodium channels close, the voltage-gated potassium channels, that being ion channels that allow potassium through but not sodium, will actually open, allowing sodium to migrate from a high concentration inside to a low concentration outside, causing through the diffusion of potassium outside of the neuron. This causes the concentration of potassium outside to increase, meaning that potassium, just like sodium, is positively charged. That means that there is going to be a stronger positive charge outside as a consequence of this. So the positive charge outside of the neuron is going to increase. Now, this means that as potassium diffuses from the inside of the neuron outside, there is less potassium and therefore less positive charge on the inside, and therefore the positive charge on the inside decreases. Now, if this means that there is less positive charge, remember that all positive charge needs negative charge in order to counterbalance it, and as the potassium diffuses outside, as the positive charge gets weaker, that means the negative charge on the inside of the neuron is going to get stronger, and that means because we have more positive charge on the outside compared to the inside, and because the negative charge now predominates on the inside, we can now say that our membrane has been repolarized because it now has a positive side and a negative side as a consequence of the potassium diffusing out of the neuron. The problem is that this neuron is not ready to function yet, because if we remember how the stimulus works, the stimulus still relies on the movement of sodium ions moving into the dendrites, but remember that the sodium concentration is still isotonic at this point, which means that sodium will not migrate into the cell to the degree where it's strong enough to trigger the threshold voltage. So the problem is, if the neuron wants to fire again, this means that sodium and potassium ions are actually on the wrong sides of the membrane, because remember, at resting potential, we want a higher concentration of potassium on the inside and a higher concentration of sodium on the outside in order to get back to resting potential. And now we've basically created the condition where sodium and potassium exist in relatively isotonic concentrations, which means we need something to take the potassium that just diffused outside and bring it back in, while taking the sodium that is inside of the neuron and pumping it back out. And that word that I just used kind of gives away the game. Because if you remember the final example of a transport protein that is used, the sodium-potassium pump, this is our solution. So the first thing that the sodium-potassium pump does is it takes 3 sodium ions from the inside of the neuron and pumps them outside of the neuron, therefore resulting in the concentration of sodium decreasing on the inside, while after having pumped them outside, it would cause the concentration outside to increase as a result. Now, after every time it does this, it is also able to grab 2 potassium ions from the outside of the cell and pump them back inside to the neuron, resulting overall in a decrease in potassium concentration outside and an increase in the potassium concentration inside. Now, what this means, we can see that overall it would result in the movement of sodium from a low concentration to a high concentration, thereby resulting in the concentration of sodium outside with potassium on the inside, which means that this pump eventually is going to start working in the opposite direction of concentration gradients, and therefore requires a constant supply of ATP in order to supply the energy that does the conformational change to require this protein to keep functioning. But as long as there is enough ATP present, the pump is active and is able to reset not only which side is the positive side and which side is the negative side, but also which ions are located on the right side of the neuron's membrane in order to keep it functioning. So the point is, after the repolarization, the diffusion of potassium outside of the neuron in order to rebalance the positive and negative sides of the membrane, the final step is to use the sodium-potassium pump to flip the ions back to their original position and guarantee that the neuron is in the correct starting position in order to be able to operate. In the final video in this series, we're going to look at the effect of myelin and how myelin results in a faster transmission of action potential compared to how an unmyelinated neuron would work.